Mhm. Mhm. Yeah, it is visible.
Okay, should I start now?
Yeah, you can start.
Okay, okay. So the title of my paper is Synthesizing Pareto-Optimal Interpretations for Black Box ML Models. We will see what these things mean. But before going into the formal details, I would like to have an example. So the example briefly stated is a neural network called TaxiNet. It was developed by Boeing, the company Boeing, that uses camera images that estimate something called cross-track error, which is basically the distance of the airplane from some runway center line. And the working of the, like how the airplane module takes the decision is like something like this. So TaxiNet is a neural network that analyzes the images and gives some decision, maybe tries to alert the airplane of some danger or just give some clearance. So it basically gives a classification. And the airplane now uses something to, like some kind of module to test if that classification can be trusted. So as we can see in this picture, that there is a clear image that has been given clearance, that is highlighted by green, and there is some image that has been classified as alert. Now how does this is like a classification done by the neural network. How does the airplane know which decision to trust? The internal workings of taxinet is not available to the airplane to understand the, like how is it working. It might as well misguide it. So now we want to understand if we can really trust the decision of uh, this neural network taxinet, right? So with that motivation, we ask this question, uh, like what kind of inputs, what kind of input features, in a neural net, what kind of input features does this taxinet neural network need? So there are a couple of features that this neural network accepts as input, namely position of clouds, that denotes weather basically, time of the day, and maybe something like positioning of the airplane, and like weather conditions is reflected by number of clouds. So I have access to, like like uh, as someone who wants to design a protocol that wants to test if that uh, classification can be trusted. I have access to these inputs, and the monitoring module requires an interpretable model to understand the decision making logic of taxinet. By interpretable model, I basically mean a human understandable explanation for when the output of taxinet is deemed reliable, right? Now, use the word explanation or human understandable interpretation. What does it mean? So, in the context of neural network, I can definitely approximate it using simpler structures, like more deterministic structures like linear models, decision trees, decision diagrams, etc., which provide a more or less structured way to represent very complicated decision making processes. Now, this decision diagram, what do? They break down the decision of the neural network into a series of very, like, concise steps that are logical and we can understand. That also offers an insight into, like, that is not very opaque, as in like the neural network is uh, a black box. Contrasted to that, this interpretation is supposed to be transparent. We know everything about its working, and it gives a representation of the decision paths, the computation paths taken by the input to reach an output, and that makes it extremely useful for interpreting the model, right? So a question is, what kind of amongst these kind of this kind of explanations presented, what kind of structures do we think are like good explanations. We've for the time being, for the context of this paper, we stick to bounded multivalued decision diagrams, which is basically a generalization of the decision trees. I will explain what these things are. Just that we want to make them finite, so that we will always apply a bound on the size of these decision trees. I will come to what this decision tree or a decision diagram means. Right. So now,
Yeah, just one comment.
sure.
Can you use,
So sorry.
move a few slides earlier?
Mhm.
Maybe you will come up with an example. So they have used a simple decision tree example as an explanation. You will show that example later on?
Yes.
Okay, fine then. Yeah, so that is
Yes.
okay. Move on. Yeah, so this is
Yes.
just right now, after you introduce this, you will show the example. Yeah, okay.
Yes. Yes.
Yeah,
Yes.
okay,
So
fine.
basically, wanted to say what is a black box model, decision
Yeah,
and all.
yes.
Yeah. So since the model is treated as a black box B, we can only access the inputs, which is basically a
Yeah,
vector.
only one comment that I had in this
Sure.
earlier motivation thing was you seem to suggest that this interpretation model that it generates would be given to the aircraft system that is using it. Okay.
Hmm.
See, I mean, aircraft is not in real time using this explanation to decide or so, is it? No.
Yes. No. No. No.
Yeah, I think that clarity has to be made. So,
Okay. Sure.
what the purpose of explanation is for people who evaluate the system, okay?
Hmm. Yes.
Which is kind of, outside. It's not as though that the explanation is given and then it is used in real time, okay? It came out like that. So,
Yes.
we make sure that
Yes.
now, okay? It is
Yes.
for
I'll just note it down.
analyzing the thing, yeah? Okay. No, I'm
Yes.
recording the thing, so you don't need to, yeah? Okay. Yeah.
Sure. Sure. Sure.
Because I'm also
Okay.
timing.
Thank you. Thank you so much for recording. Yes. Now I want to understand that what is given to me. So since I'm only provided with the black box model, I only can access inputs, which is basically a set of permissible vectors, n-valued vectors for the timing I'll consider, and each input in the vector, each variable, each position is of a feature. So I can say that the input space is a subset of the feature space, and the features are numbered as f1 to fn, and each fi has a fixed domain di. And then there we have an output class, which basically tells us how we can classify the input based on the black box function. So now we for each feature I, we have some predefined partition functions that basically partition the domain, of that feature into some finite classes, and that is so we highlight that as bfi. So we will call it as a branching function. We will see how this branching function stands true to its name by actually helping us understanding how in a decision diagram this will help in the branching. Finally, we define a decision predicate, which is basically uh, takes a feature, assigns some input to it, and decides its branching by selecting some branching function from the set of all available branching functions. And so now that we have a predicate in hand, it's a multi-value predicate, right? Because it's assigning values in accordance with branching functions. So the decision diagram will basically be a DAG. I will come to that. So basically here I have tried to convey the meaning of this predicate that takes some value of a feature and then decides the branching via some branching function that I've taken up, which makes essentially P a multi-valued predicate. And by stylized P, I denote the set of all predicates available to me. Now I come to a multi-value decision diagram. So given it's a directed acyclic graph DAG, V and D are its two vertices and edge sets over a finite set of nodes V, and each internal node V has a label corresponding to a decision predicate P. So every internal node corresponds to some predicate in the set of all predicates. Please observe that I have not restricted like them to be unique. Like in a decision diagram, only the number of nodes need to have some upper limit, as I've specified earlier. It can take like more than one node can take similar labels. The leaf node corresponds to an output label, and for a internal node labeled by the feature fi, we choose a branching function and apply the corresponding predicate, making the edges basically the branchings, and the outgoing edges are accordingly labeled. So this is a multivalued decision diagram. So here we have taken one example of the taxinet with input features, that is one position, weather, which basically denotes by the number of clouds, and time of the day t. Hence, our input feature set is TCP. Our output set takes alert or no alert. These are like two of the possibilities.
Hence, I means I here is the feature set.
Yes.
Yeah. Okay. Input feature.
Yes.
Okay. Fine.
Input feature set. And the output stylized row is alert or no alert. I haven't explicitly defined P here because it will take a lot of space. Assume we have defined some predicate on like these features, POS like position, time, and clouds as the predicates, and the corresponding to the features we have defined them as actually P corresponding to P, the predicate is pause, and so on and so forth. Then these are a couple of possible decision diagrams that are acceptable as interpretations. For example, the first one that only uses the predicate time. The second one uses pause and time. And the third one introduces a lot of them with time and pause coming twice. Like they have been used as labels more than one time. So these are acceptable interpretations to the taxinet model we have just seen.
Yeah. Now here, can you explain? Maybe I know you say that B. Okay, in your definition, the difference between P and B was not clear. Okay, P
Sure.
is the predicate. So when you explain it here, okay, I think you should spend a little bit of time as to how to interpret this decision tree. Go to the next thing. So time is a predicate. So time, so you said it's multi-valued. The multi-valued thing is only at the leaves, like alert, no alert. There you can have, here is one of two possibilities, but in general, you can have multiple outcomes, correct? That's what
Yes.
that
Yes.
you could mention, yeah? So,
Yes.
but each of these are predicates, which means they can only have true or false, okay? So, but here, if it is a predicate, you can only have true or false.
Yes.
But here you have multiple edges. What does that mean? Clouds,
Yes.
so you have to explain. So, if you say pause and clouds are predicate, then their outcomes, usually a predicate, the outcome will be true or false.
Yes.
Right? So, but then there are four here. What does that mean? Okay.
So, yes. Should I explain now?
Yeah, please explain to me
Sure.
now. Then,
Sure.
I'll ask question and then you could make it clear. So there is
Sure.
some relationship between B and P, which you did not. Okay, first explain to me on the network, I mean, on the example, and then,
Yes.
I'll come back and question the B so that you will be able.
Yes.
So
So,
what does it mean here?
So clouds, I'm taking clouds as an example.
Yeah.
So in the third example, clouds denotes the it basically is a predicate for the input feature C. So I have restricted C to take values from 0 to 5. Like these are the input values I can give to C. Now
0 to 5. So
yes.
okay. So which means if it is if clouds is 0, 2, or 3, it is true. When is clouds predicate true on its
So
value?
the thing is, here I define clouds as a multi-value. Like all of these are multi-valued predicates. So they do not necessarily take just 0 and 1 binary values. They can take multiple values. So that's why the partitioning BI function, the branching function comes. That partitions the domain of the feature into classes, like not just two classes, multiple classes. And
So in a way, clouds is not a predicate, okay?
okay,
Clouds is, you could say that, clouds, the value of clouds is either in partition 1 or partition 2, partition
yes,
3, and partition 4, okay?
yes,
That's how you would define, okay?
yes.
Yeah. So why do they define it as predicate? That's a little bit confusing. Yeah.
So
Yeah.
they
Yeah.
keep
The
on mentioning it's a
predicate.
multi-valued predicate.
Well. Multi-valued predicate. See, multi-valued predicate. It could be 0, 2, 3, and what it's checking is if
Hmm.
the value of cloud is in partition 1, partition 2, or partition 3. Okay, that's
Yes,
what it is. That's what it's checking. So as a predicate, you can view it as, if it is in partition 1, only this will be true. Okay. If it is
yes,
or if it is partition 2, which is 4, then this will be true. So in that sense, clouds is a predicate. Okay.
hmm.
It's saying multi-value. Okay. One way is to say multi-valued predicate, but it is really checking if the value of cloud is in one of those partitions. Okay.
Hmm.
So
Yes,
then only one of them will be true. Either this can be true or this can be true. 0, 0,
yes,
0. I mean, this can be 1, all the rest is 0. Okay.
yes.
So it can never be the case that two of them can be
True at the time.
simultaneously true. Yeah. So in
Yes,
that,
yes, yes.
it is predicate. There's a multi-way branch because for the different values for which it is for which it is true. There's only a unique partition for which it will be true. So the
Hmm.
predicates are over whether the value lies in a particular partition. Okay, that's what. Huh?
Yes, I understand that.
Ah, yeah. So in this case, here there are 3 partitions. Okay, then you could explain it. Okay, instead of
Hmm.
saying it's 2. So there are pause is the pause is a predicate over the feature, and that feature is based on the feature value being the value being partitioned into 3 partitions. Okay, one if the feature takes the value between 2 and 5, or if it
Hmm.
is less than, and so on. Okay, there are 3 partitions, and
Hmm.
this is true if the value is in if the value of that feature falls in that particular partition. Okay,
Yes,
correct. So you could explain it like that. Now, so then
sure.
it will be quite clear. So it is a predicate. It is kind of not exactly correct to say it's multi-valued predicate. It's the predicate. See, it can never be the case that two of them can be simultaneously true. Okay. So,
Yes,
I mean, it's multi-valued in that the number of branches will be the number of partitions. Correct?
yes, exactly,
And the value can be in one of those partitions. Viewed as
exactly.
predicate, it says, am I in partition 1 if the given value is in partition 1, partition 2, or partition 3, or partition 4? That's all.
Yes,
That's how it is doing. So why don't you
yes,
explain it like that? You take the
sure.
opportunity of that thing saying, yeah, see, B is actually the predicate. Okay, P is a function. B is actually checking if that one is in that partition. Okay, correct.
Yes,
Yeah.
I understand. I'll modify this part.
No. Here all it is correct. I think you could take an opportunity
Hmm.
to explain it here. Okay, each of them is a predicate, and the predicate is checking if the value, the input value,
Hmm.
is in a particular partition. Okay,
Yes,
the partition is fixed, right? Huh?
yes.
Or
The partition is fixed.
oh, no, that's actually not true. So the partition may not be fixed. See, the partition is
The
fixed.
partition is fixed.
Okay. Now that's actually not true because, for example, pause in here, on the right side, takes checks three-way.
Yes, and here it
Whereas
checks two.
here it's only two-way. Okay.
Uh, yes.
So here it's only two-way. Therefore, it is not. I mean,
I mean, there is a
each
upper
instance
limit
of
to
that
it.
predicate can have a different partition, right? Here it is all of them greater than 2.5, or it is between
Less than 2.5.
less than 2.5. There's only two partition for that instance of cause predicate, whereas here there is.
Also, here is one thing I just wanted to mention, Professor. So there are different branching functions. The left on the I define like the BF is like a set of branching functions. Maybe here in the left side, the function branching function that is used is different from the one that is applied on the right side.
That's what I'm saying. Which
Yes.
means, what do you mean by the branching function? The B is what you call as the branching function?
Yes.
Yeah, but that depends on the number of partitions, right?
Yes.
So here there are only two partitions that you are concerned. Huh? So here it's a two-way branching, whereas here it is a three-way branching. So it is not fixed, is all I'm saying. Okay. But different predicates, for different instances of the same predicate, the branching can be different. Huh?
Yes, agreed.
Yeah. Okay. So that's, yeah. So in that sense, this predicate is, you can either have greater than 2.5, less than 2.5. So, so here it is less than 0.5. Is it less than 0.5? Here it is between 0.5 and 3.5, greater than 3.5. You see, it is.
Yes.
So it is kind of total in that sense. It is, that's why you call it a partition. So different instances of the same predicate can have different branching function or partitioning. Okay, that's all. Yeah, you can bring that.
Yes.
Yeah.
Yes. I'll mention that. Thank you. Should I move on?
Yeah.
Okay. So now we want to understand this question: are all explanations equally good or useful for that matter? So we take these two examples as we have seen, like the one with like just a decision tree on the left. It just takes time as a predicate and branches into no alert or alert. It does not look into anything else, position of the airplane, number of clouds, etc. It does not look into. So
where have you defined an explanation? So where have you defined an explanation? Have you defined an explanation here?
Yes, above. Should I go to that slide?
Yeah.
Yes, here.
No, but this is not a formal. Hence, a bounded multi-valued ASIC decision diagram as explanations to the neural network. There's no formal definition. I mean, it is just this, and you're giving an example of. Yeah, I think. Okay, what I suggest is, before you introduce this example, okay, go to the example slide, because you don't have a slide which has your formal definitions are mainly for decision tree. Okay, so here, before you introduce this thing, what you can have is show a DNN. Okay, there's one single DNN with inputs. Okay, as what are the inputs there? Okay, position, time, correct?
And clouds.
And clouds. Okay, those are the inputs. Then there is a box. The output is alert or no alert. Okay.
Yes.
And then now you have, go to the previous one. Okay, I think when you introduce you have actually done here. But what I would like to see is that this thing is the cloud, time, and CMP are features. Okay, each of them have those values. Okay, it's much like the way Aritra had it.
Yes.
And what these things take is the values are actually the cross product. Okay, it's the same thing. So in that sense, you could say TCP, they are the features, but they take values. Okay, so you draw one picture here. the DNN picture.
After this slide?
No, in the slide itself. Okay.
Okay.
So you can kind of insert it right here, okay, as another, you shrink this and then have the DNN, okay?
Yes.
Now,
Sure.
now you see, and you can say, look, there are three possible explanations as decision tree for that explain the behavior of that thing, okay?
Yes.
Huh? So
Yes,
that will reinforce, because see, you long time ago in that kind of verbose slide, you kind of snuck in what an explanation was, okay? So they would have, it never registered in the audience. So now you could make it a reinforcement. There is a DNN, and these are
other explanations
that are trying to explain the behavior of that, okay?
Okay.
This could be an explanation. This could be a little bit more detailed explanation, even more detailed explanation, okay? Take the opportunity to reinforce that, okay? As well as how exactly the trying to explain your definition of decision tree, all the details about partitioning, because the partitioning part of it, you can only explain it here. I mean, you can very clearly, okay? So here, the position has a three-way partition on its, features, okay? I mean, the feature values, right? I mean, feature is position itself is a feature. So value space is partitioned. It's a three-way partition, okay? And here you can see the clouds is partitioned 4 ways here and so on, okay? That's given, okay? Yeah.
Sure, I'll definitely do that.
Yeah. Okay.
Diagram here.
Now that'll make it very clear. Okay. Any doubts that they had? Mainly two things. Okay. There is a single DNN. There can be multiple things. Okay. And then how exactly decision trees are to be interpreted. Okay. Yeah.
Yes, I will do.
Okay. Go ahead.
Sorry. Okay. So having said that, now we want to.
Now it makes sense. Are all explanations equally good? Okay. Good. Yeah.
Yes. So explanation 1 has 3 nodes, and explanation 2 has 7 nodes. So to a human, rational human being, it's easier to understand explanation 1 because it does it. It has just 1 node. But to like understand how explanation 2 is working, I have to like keep a track of so many decision paths, right? So it is very difficult for me to understand as a rational human being.
Yeah. So here in the title, maybe you could make it as correctness. Okay, these are two different aspects of an explanation. Correctness versus understandability. Okay, put that as understandability. I mean, you could say, yeah, because that's what you're saying. It is difficult to understand. So there is a measure of understandability, which is you measure in terms of the size. Okay. And the correctness is how well it predicts the behavior.
Yes.
Okay. Now, where do you explain correctness?
In the subsequent slides.
No, but you are already saying correctness versus explainability. So without actually explaining correctness, why do you say?
So in the very next slide, I say what I mean by correctness.
Okay. So you should say, when in words, I mean, you will define correctness, okay? Explain understandability is measured in terms of the number of nodes, correct? Or the depth, I don't know how else. More predicates, more nodes, harder to explain. Explanation was simpler, but omits key features like position close are less likely to be predict correctly. Okay, then, yeah, you should say correctness means how well this this interpretable model predicts, how accurately it predicts the original behavior, and understandability is how easy it is to read. Okay.
Yes, I will mention this thing.
Understandability, or maybe you could say explainability. That's okay too. Yeah. Because there are two factors under which you could measure how good they are. One is how accurately they are doing it. That is correctness. The other one is how easy it is to understand explanation, which we call as explainability. Okay. Yeah.
Yes. Sure.
Then now
also,
the next slide. Yeah. Go ahead.
Just one thing I wanted to know, Professor. Since you have been so the thing is, can I have a small script with like this suggestion that you said? I I have practiced, but I might forget some of the details that you asked me to explain verbally. So, like, can I just have pointers regarding those
No,
things?
no, 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 no. I'm recording it.
No, no, I'm saying like during the presentation, can I have like some small pointers regarding those things?
I will definitely do that. Okay. Like what I'm
Okay.
saying is, I'll see there are two kinds of questions that I will ask.
Hmm.
Okay. One is soft questions. I ask is soft questions. Okay. Soft
Mm-hmm.
questions are when something is not very clear in your thing, I will deliberately ask that question to make it so that you will make it clear. Okay.
Sure.
That's what you're saying, right? During
Yes.
presentation, ask those questions. And then hard questions are, which are usually come at the end, okay,
Mm-hmm.
where, or at critical points in the thing, where it'll be those questions to check if you actually understood the material. Yeah.
Sure. Sure. Sure.
Yeah.
Sure. Thank
So
you.
what you're asking, what you're suggesting is that I ask those questions if you have not made that point, correct? During the
Yes.
presentation. Yeah, that I will definitely do. That I
Sure.
will do for everybody. Yeah.
Okay.
Yeah.
Thank you so much.
Go ahead.
Yes. So
So far,
now that
so far quite good. Yeah.
I have asked the question, are all explanations equally good? So I want to quantify these measures. Like, what do I mean
Yeah.
by explainability? I have just given a very subjective view,
Mm.
explainability, correctness, etc. Now
Mm.
I want to quantify them. So
Mm.
how to quantify these
Formally,
parameters?
you quantify them or you formalize them. Yeah, quantify them.
Yes,
Fine. Formally quantify them. Okay.
sure.
These parameters of correctness. Good. Good.
So given a decision diagram uh, E, we have
Yeah,
two associated.
one more point. Right
Sure.
at that point of in the previous slide, you could kind. I mean, I'll ask that question. How will you contrast this with the explanation as because you will follow Aritrag, okay?
Yes,
Ask how is it different, okay? And
sure.
then you explain it, okay?
Yeah, yeah.
This is doing an all inputs, yeah,
Hmm.
and it is
Hmm.
coming up with a model, which we have already done. So those are the two ways, yeah, in which it.
Yes,
Go ahead. Yeah.
yes. Yes. So now I want to formally quantify parameters, correctness and explainability. So given a decision diagram, we have two associated parameters.
Mm.
Uh, One is correctness in the traditional ML sense. Correctness basically means with what precision or what accuracy my model can predict what I intend it to predict. So
Yeah.
one,
How accurately it predicts the original DNN behavior, correct?
yes,
Yeah.
yes.
Mm.
So, and for the purpose of this paper, the authors have selected the measure delta C as accuracy amongst all other features, amongst all other classifications. We have selected accuracy. So, when we are given a set of samples which we have taken from the original DNN S as input output pairs, we quantify this correctness measure using two parameters E and S as a number of input output pairs in the sample S such that uh, our interpretation agrees
Mm.
on that sample
Mm.
divided by the number of total samples. So basically, with what probability our interpretation will predict a correct uh, IO, a correct output on an input from the sample space.
Yeah. Okay.
So this
I,
is
I know you have it as IO here.
hmm.
Can I make a suggestion to have it as uh, O applied to DNN of I? Okay.
Sure, sure, sure. I'll
Yeah.
just
Or
copy.
you could keep it and say have where O is equal to DNN of I or F of I, whatever. That function is on the original thing. Okay, there are two things here. Okay, one is it is defined based on a set of samples, and
Hmm.
the IO pair is actually the O is actually the output produced by the
By the
original.
DNN.
Okay, that you can make it explicit here. O is equal to DNN applied to I. Okay, so that is
Yes.
very clear. Yeah, that is
Sure, sure, sure.
yeah. Go
Thank
ahead.
you. I've noted it. Now coming to the term explainability. So what do I mean by explainability? Explainability is classified as a function that associates a weight W with each predicate with the following properties that the user might find some predicates to be more favorable than the others. Maybe somebody finds the number of clouds, the weather to be a more like better classifier, a better input than maybe what the position of the airplane. So the user is expected to indicate their preferences, and the weights will be consistent with that. So whatever favorable predicates are there from the user, I will give them more weights as compared to the ones that are less favored. And secondly, I want my decision diagram to be precise in the sense that there are not a lot of nodes, not a lot of nodes used in the diagram. So I will reward predicates with less branching, with that use less branching factor functions. And lastly, how do I quantify it? So I like basically take like the predicates and multiply. It's a linear function of
Wait
the
a minute.
weights.
I mean, there is something wrong here. This
Yes,
is
yes, yes. Actually, yeah, this should
delta
be the weight.
E is defined in terms of delta E.
Yes, this should be
Recursive.
the weight.
Huh?
This is a typo here. This should be the weight.
Oh. Then you should use a different function for weights, no? So
Yeah, this should be a
delta
weight. This is a
E
typo here.
should be weights. Huh? Which
I
is
intended to write WP. I'll fix it right away.
this is WP.
Yes.
Again, what is the second delta?
This second delta is supposed to be WP. This is like the predicates like explanation factor.
No, but you are not defined what WP applied to explainability itself is.
Yes.
No, there is something. Can you show an example? I hope you should have an example, okay? On your original thing, tell me, given some weightage for the predicate, how exactly? Do you have an example?
About this, I don't have an example.
No, you should, okay?
Okay.
Because I think having an example will clarify the question that I have. Okay, let's take the simple thing. So, first of all, delta E is a measure of explainability. That is somehow defined in given certain weights to each of those predicates. And given a particular explanation, okay, as a decision tree, which is the structure, and the weight for each of those predicates, there is a formula to compute the explainability measure, delta E.
Yes.
Correct? Yeah?
Yes.
Now, that is very clear. How is it? Go back to one of the examples and tell me how it is. What
Yes.
would
So the approach that I understand is to build recursively. So this explainability measure first associates a value with each of the predicates.
Okay.
And
that's the weight.
That's a weight. Yeah. Weight. A weight with each of the predicates, and maybe
so let's suppose the weight is the same. Okay. In this case, let's suppose the weight of time is something, and weight of, I mean, you can take the simpler one. Okay.
Sorry. Maybe I'll just write it. So time is 1, and
do you know what it is, or do you have to go to the paper? Okay.
No. Like I can take any, like this is user defined, so I can take any input.
Yeah.
So I'll just assign like random things. Time 1, position 2, and maybe clouds is more important, so it's 3.
3. Okay.
Yes. So
then what is the delta E for this?
So delta E for this structure, I'll call it eta, is basically 3 plus 1 plus 2 plus 2 plus 1.
But in your definition, 2 times this.
Pardon?
No. You have it. Oh, I'm sorry. This 2 is with position. So it's just a summation. 3.
Yes.
You go down the tree and then you just keep adding. Okay. You just traverse the tree. 3 plus 1 plus 2 plus 1 plus 2. Okay. But somehow you had some multiplication, etc. in your form.
Yes, that was like a typo. Like it just got copied. I need to fix that. That was a typo. I need to fix that.
So it doesn't take into account the depth of your tree, of your decision tree? No.
That is taken care of by, so when I'm like this weights thing does not take into account that. So when I'm assigning, just a second. The depth of the tree So when I'm assigning functions, I'm that is just
So how
reflecting the
would you
preference
do
of the
this?
user.
So this is just okay. So your equation ends here at the
Yes, this
at the
is
period, and this should be in the next line. That was the mistake.
yes,
There's no multiplication or anything.
yes.
Okay, good. So so then this should be
It's like
weight.
the full stop.
Okay?
There's no multiplication.
Weightage for the predicate. That is fine. Okay.
Hmm.
So now then it becomes clear. I don't think, I mean, maybe you can use that as an example or so. But my question is, so in that sense, it is just a function of the number of predicates. It is somehow a function of number of predicates, not
Yes.
in the depth of the tree or anything. That is not taken into account.
So one comment I have to make here is, since I'm bounding the it's a function of the nodes, right? Number of predicates, and it's a tree. So I can always say the
No,
depth
no,
of the
that
tree is
is if
limited
you're
by.
assuming a certain way of assigning the weightage. The
Hmm.
more branching, you assign more weightage to those predicates,
Hmm.
then the branching is taken into account. Okay,
Yes.
not necessarily certainly if you have deeper, there'll be more nodes and therefore it will be higher. Okay. So
Hmm.
I guess so. I guess correct. Okay. I think observing something of that kind would be useful. Yeah. I think what
Yes.
you're doing is there are two things here. One is the explainability measure is computed as a function of the weights that you give for the various the nodes in the tree. Okay.
Yes. Yes.
And the weight that you give for the predicate itself, I mean, for the nodes, which are predicates, is dependent on in these two factors. Those are two
Hmm.
separate things, okay? And
Hmm.
then overall, the more number of nodes with more weightage, the higher your understandability is. Okay?
Yes.
So in some sense, it is also a function of number of nodes. And
Hmm.
the number of nodes in an explainability is also, a function of the depth, though both
Yes.
are taken into account. Okay.
Hmm.
So now it's clear. Yeah. Okay.
Yes.
Yeah. Maybe
So
you can bring back that slide and then show what for a given weight, like you said, what
hmm.
the weight for these two things are. You put
Yes, I'll include this picture.
then it'll be clear. Now let's move.
Yes. Yes. Yes.
Okay, because you have to finish at 12. Okay.
Yes, 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 sure. So the goal is to come up with a good, which is basically correct and explainable interpretation. And I have just highlighted the good part. I have not defined it. I'll define it what means to be good. So the question is, what constitutes a good interpretation? Now, given any interpretation,
You want to use good or okay, you use good and then you come up with Pareto optimality. That is your
yes,
measure of goodness, correct?
yes, yes, yes.
Okay, fine.
So the pair delta C and delta E induces a partial order on any set of decision diagrams given a set S of sample, basically.
Mm.
So the partial order I have defined here is like some E1 is getting like is preferred over E2 if both of its parameters rank strictly uh, less than equal to like either one is strictly less or equal to it. So that's how the partial order is defined.
Mm.
Why do I say this is a partial order and not a total order? Because when just one parameter increases and the other decreases, I do not know how to compare them. So
Yeah,
that's why
yeah,
it's a
I
partial
mean,
order.
that's true. So because that is kind of obvious, okay?
Yes,
So
yes,
you
yes.
have a pair, each of which is ordered. The pair can have, unless you could make it, I mean, you could use lexicographic, okay?
Hmm.
Then it can be, no. Even then, if you use lexico, it's not like it is in general a partial order. Okay, that's
Hmm.
all. Yeah, you can make it to be total by using lexicographic order.
Yes,
Okay,
I can extend that.
yeah. But anyway, so in general, it's a partial order because it's over pairs. Okay,
Yes.
yeah. Okay.
So now I define Pareto optimality. We know that every partially ordered set contains a maximal chain, which also has a maximal element, that is Zorn's lemma.
Mm.
And some interpretation is Pareto optimal if
Mm.
its parameters are maximal in some chain according to the ordering induced by
Yeah.
this pair.
Okay. Fine. Yeah.
And basically I want to find a set of like some E in that max X, right? Now I have a graphic
Very
description
good.
of what.
Yeah.
Sorry.
This is very good, I said. Yeah. This is
Okay.
what I was hoping that you had. Okay. So you say you gave the explanation. So you can move on. Okay. So,
Sure.
I believe you. I trust you that you can define that. Okay. Now, good. Problem definition. Fine. Yeah.
Yes. So
Yeah.
now I define E to be the finest class of interpretations over inputs and outputs O, and S is the sample. And I already have these two things defined to be correctness and explainative measures. Now, basically, by Pareto optimal interpretation synthesis problem, I want to find an interpretation in E that satisfy the definition I just said earlier. So that is the problem. Now,
Yeah. Now, why should E be a finite class of interpretations? Given a finite I and a finite O, a finite set of predicates, features, there is always going to be a finite number of interpretations, correct?
actually, no, because I can repeat predicates, no? So I can like just go on infinitely building some decision diagram.
I'm saying, uh, yeah. As long as there is no. We are assuming there is a bound on the depth, which you already said.
Yes,
Okay.
yes.
Given a bound on the depth, then only finitely many. Correct. If all the other things, correct. Yeah. So this whole thing is the search space is that, isn't it? Yeah. It's
Yes,
not
yes,
that
yes.
you're given a finite. See, if you bound the depth and your features and the predicates are all bounded, obviously, okay, then there are only finitely many possible interpretations. Correct.
Yes.
Yeah. Syntactically. Yeah. The delta C and delta E of those things can be different depending upon what your weights, etc. are. Okay. Yeah. So in that sense, even when the weights are fixed, they're only finitely many. Okay.
Yes.
So that's so yeah, and your Pareto optimal synthesis problem is actually over a finite set. Okay.
Yes.
Yeah, you see, otherwise even max sat, etc. won't even work. Okay. That is
Yes.
so what is this is a good definition. The confusion is let E be a finite class of interpretations. It gave the impression that you determine a priori what that E is. No. Okay.
Yes. I do not want to define that.
Given a bounded depth, there are only finitely many syntactic interpretations. Okay. Now, and given a weightage, then this problem is a finite search problem. Okay.
Yes.
Yeah. Okay. Yeah. I mean, I want you to understand that. Yeah. And
Yes.
that's
Should I make any update here?
No. I think the update will be to change that. I mean, make an observation before this saying that, go to the previous slide. Yeah. So here you can make an observation that, look, as long as we limit your explanations to have a, bounded depth, and which can happen only, and the number of predicates, I think there's only finitely many explanations. Okay.
Yes.
Yeah. Then you can keep the other one. Yeah.
Okay. Sure. And I'll do that.
Yeah. Here, the only thing is I'll say let E be the set of all finite class of interpretations over inputs I and O. That's what I would say. It's a set of all. Okay. And that set is finite. You already said. Yeah. For the reasons.
Yes.
The only thing a change I'll make is let it be the set of all.
All finite. All
interpretations, which is finite. Yeah. Yeah.
Yes, which is finite. Yeah.
Go ahead.
That would be a better way.
Yeah.
Yes. So now I want I want to see how to solve this problem synthesis via weighted maxat. First, I define what do I mean like the weighted maxat problem, and so given a clause, so given a formula in CNF form, which has like m clauses, each with weights, we want to find an assignment.
At this point, once you have defined the problem definition, I'd like you to put an outline. Okay, outline slide. Saying what are the main parts of the rest of the talk. Okay.
Okay.
You can say that this is solved by maxat. Okay. You first define maxat. After that, how many more slides are there?
There are 14 more slides.
14 more slides. So what are the main things? Okay. So you will define maxat. Okay. Once you mention that it solves this problem using maxat, you will introduce maxat. After that, what are the broad things that you will be discussing?
Firstly, how to come up with one single Pareto optimal solution using maxat. Then coming up with all possible Pareto optimal solutions given a range. And lastly, a statistical guarantee of the sample size I need to take. And concluded with some experimental results.
Yeah. So first, introducing maxat. Second, how this problem of finding a Pareto optimal E, okay, can be encoded as a maxat problem. And then solving it, how much sample that you have to have in order to give certain guarantees about the quality, correct? And then experiment.
Yes.
Fourth, okay, put that.
Yes.
Okay.
Okay.
First,
Okay.
introduction to maxat. Second, how do you encode it? Okay, but that's the big thing, huh? Okay.
Yes.
How do you I mean, what is maxat and how do you encode it?
Yes.
And then what? And then how many?
No, then I want to find given I say I have found already one PO solution using maxat. Then I want to find more such solutions, possibly all such solutions given in some range. So there is some steps for that, like dividing the space into
Yeah.
like
Okay,
that.
fine.
That
So that you put that outline slide. Now you're saying weighted maxat. Okay.
yes.
Now go ahead.
So I've basically defined weighted maxat and also given a variant. I use a variant of the problem here. That is basically I have a set of hard clauses that must be satisfied and a set of soft clauses which does not need to be satisfied as a whole, but their weight should be maximized. So that is the thing.
No. Your explanation was not very clear. Okay. Unlike original SAT gives a satisfying instance. Okay. So maxat gives a satisfying instance such that every hard must be satisfied, and the number of soft clauses that need to be satisfied, it maximizes this
The
one.
weights.
Okay?
Yes.
So
Yes.
emphasize the fact that not all clauses need to be satisfied. Okay, that did not come through. Okay.
Okay. Okay.
Unlike SAT, here it satisfies as many clauses of the soft clause to maximize the
Maximize
soft.
the weights.
Yeah.
Okay. I'll mention that. Unlike SAT,
Okay, no, go ahead.
it tries to maximize. Yes.
Speed now. Yeah.
Yes. So before going into the encoding,
No. You didn't explain how it was encoded. Okay.
Yes, just before going into the encoding, I wanted to prove that a weighted maxat problem instance.
No. You won't have any proof. Okay. What is the proof that here?
That every solution of the weighted maxat problem on this is a solution for the Pareto optimal synthesis problem.
No, but that requires your encoding, no?
Yes.
So why did you skip over the encoding part of the previous slide?
Actually, no, there's encode. Actually, this got a bit mixed up. This slide is intended
Go back to the slide.
Yes, this one.
No, where you introduce maxat.
Here.
You have something like here. What is this?
So yeah, this part, right? The blue box.
Yes, you're not going to explain it here?
No, I am going to explain, build up all the encoding in subsequent slides.
No, I think top down would be better. Okay. So you make, I think top down solution would be better. Okay. So you could do it by making what is phi E, what is phi S, which do you think is a better encoding? I think this would be better. So you certainly want what is phi E, what is phi S? You can explain it, okay? And then you could introduce how you encode it, no? So
yes.
Given a set of samples, okay, what does phi E? Explain what phi E, phi S, and phi delta C informally, what they mean, not in terms of formula, but rather in English, okay? So I would split the slide into two. One is just maxat, okay? And how you could, at the top level, encode this as a MATSAP thing. I mean, this deriving a possible solution. You see, maxat, a solution for maxat itself can be multiple. I mean, SAT also has multiple instances. maxat also has multiple instances. Okay, yeah, because they can be, different possible solutions that all maximize the same thing. Huh? Correct? Yeah. So that is
Yes.
fine. So I'm saying use top down. Okay. So
Okay.
describe what phi E, phi S, phi delta C is. Okay. Formally, maybe you have that. What is the previous slide? No, next one. Yeah. See, but how will you even prove this unless you have?
So this is a mix-up. This was supposed to come after the definition.
Okay.
Yes, this was supposed to come
No,
after that.
okay. But what I'm saying is you have to have a slide. Okay. Go to the previous slide, split it, this, okay, the max that, and then you can, explain the thing, split it, and then one slide which explains how you're encoding at the top level with description of what phi E is, what intuitively, what is phi E?
Okay.
Tell me.
Yeah. So intuitively, phi E basically tells us given like how like given some set of predicates, what kind of like how do I want
Yeah,
my
that
structure to look?
actually phi
So
E is a legal, syntactically correct explanation. Okay, that's what phi
yes,
E does. Okay, simple, very simple. One line sentence explains it. Okay, it
legal.
encodes that whatever explanation E that it generates is a syntactically correct explanation as per the predicate. Because each predicate has certain branching, etc. There are certain syntactic constraints. Okay.
Yes.
That's what phi E does. Phi S does, given the sample, okay, that it, what is it? I mean, it has to, whenever,
Input is given on the syntax, it gives like that output.
yeah, that it indeed gives the output, okay, for each of the input, whatever output that it gives. Yeah. Now, these are the soft one, okay, because that is where you want to search which is more optimal. So phi delta C, computes the correctness measure, okay,
Yes.
for any particular solution. Yeah, and E
Sorry.
computes the explainability, okay,
Yes.
measure. Okay, so that you want to optimize over. You can never compromise on the first two things. Okay, yeah, this yeah, right. Okay, so okay, so phi E is syntactic constraint. Phi S is semantic constraints. Okay, exactly.
Yes. Semantic constraint.
Yeah. So that's what
That's a
you will.
nice way.
That is semantic constraints. These two are saying that, given a C and an E, it will check if it is, the soft constraints are that indeed, the C, given a C and E, that they are, that they indeed are the measure. Okay. That's how. Now, any solution to it will be a particular, CE that will do. Now, we have to figure out, and when you maximize it, we get optimal solution. Yeah. Okay.
Yes.
But that intuition, even if the rest of your thing they don't understand, they will understand how exactly it is being solved. Okay. Have that
Yes.
slide. And after that, now you continue. Okay. Yeah.
Yes. Uh, sure. I'll come to this proof later. It was supposed to come later.
Yes. Okay. How
So,
to, yeah.
yeah, now I want to understand how to encode E as a Boolean formula, satisfied the problem. So, I denoting K node decision diagrams over the predicates I have and the output labels. And it's a conjunction of three things. Firstly, all nodes, internal nodes are assigned a predicate. So I denoted by this that lambda IP denotes that node I is labeled P. And it's an exhaustive thing that denotes that the first constraint, that for every node in 1 to k, it has at least one label.
Yeah. Can we do one thing? Okay.
Sure.
I want to go through quickly all the slides you have, the rest of the slides, and then I will give you an overall thing, comment. Okay.
Yeah.
This one,
I'll
how to code and phi is one. How to code,
yes.
go to the next
Phi
one.
s
Code and phi
is
s.
one.
Then,
Then I just briefly mentioned this key, which is hard clause and which is soft one. Then I show how to encode
but
delta C.
that is not necessary because you've already, if you introduce the slide in the top level, you already done that. Okay.
Yes. Yeah.
Then what? How do you encode the phi delta C? How to encode phi delta C? Yeah.
Yes.
And
So then I show how to encode delta E, like the
yeah.
explainability constraint.
Yeah.
And then yeah. So basically, since I've already said in the earlier stage, the proof was supposed to come after this. So
No,
I
no,
just
no,
got
no.
up.
Okay, so let's see. No, go ahead now. Next, there was some example. What are you doing? What are you doing here?
So basically, now I show why do I need the full Pareto frontier. By synthesizing that formula, I can have one solution. But here the top solution has explainability and C. Explainability is low, but
What do you mean
correctness
top
is high.
solution? This is what this is the one which has the maximum weight. Okay, combined
Yeah,
weight.
yeah.
Yeah.
Top by like the topmost one, like
Yeah. Okay.
at the topmost corner.
Yeah.
Yeah, and the bottom solution is vice versa. Like it has high explainability but low correctness. So now we need to exhibit all the Pareto solutions so that the user can choose which one to focus. Like there is some subjective measure of like preference involved here. So just exhibiting one solution is not really helping us. Now how I show how to like synthesize, like what this Pareto optimal solution does is it breaks the solution space into 4 regions, while R2C R2 does not have any pure solution by definition. R1C cannot have pure solution as that contradicts Pareto optimality of C. So if I want to look for
in your previous slide, what do you these are all, each of them is a Pareto optimal solution. What is a Pareto optimal?
Yes.
Why is it? I mean, where have you defined Pareto optimality?
In the previous slides.
Where?
Yes, here.
It's some maximal thing. Yeah.
Yes.
Yeah. And then that you have explained with respect to the example also, correct?
Yes.
Yeah.
Yes.
So then you could, without proof, I mean, you can have proof depending upon a time, okay? And now you could explain that each of the points there is every maxat solution is a Pareto optimal solution, correct?
Yes.
Yeah. So you could, but you want to find but computing all possible, there are lots of solutions, okay? And then you could run maxat, enumerate all of them, and you get all Pareto optimal, right?
Yes, that is one solution.
Yeah, but that is not what you want to do. You want to do it efficiently.
Yes. Yes.
Right? So using maxat, you can get all of them, okay? Correct? Then
yes, I can
then why do you need to split into these quadrant, etc.? Why?
So by using maxat, I can get over all decision diagrams, and that is exponential in the number of predicates.
Yeah. Okay. That is the point. Okay.
Yes.
That you did not mention. Okay. So yeah. So your next problem is you have already done maxat. You have shown encoding. So it's fine. If you can enumerate all of them, you can get all of them. Okay.
Yes.
That is too expensive. Therefore, the next thing is how can I devise a procedure that can more efficiently zero in on with some hyperparameters, some among all the Pareto optimal, something that you care about, right?
Yes.
Yeah, that is the second one. Okay. So in here, you can put in that slide on the correctness. Okay. That everything is Pareto optimal, the one that you have. Yeah.
Yes, the proof.
Good. Good. Okay. Now, okay, go ahead next.
So now I show how to like given a.
This is where you have to now define the second. Okay, you already had an outline. Okay. So there, the first one was maxat, how to introducing maxat, how to encode, and showing that Pareto optimality. I mean, solution is a maxat solution. Okay, that's done. Next thing is synthesizing Pareto optimal interpretations more efficiently. Correct? Yeah.
Yes. Yes.
Yeah. Iteratively explore these regions so that you will. I mean, is it true that that every maxat solution is but depending upon okay, if you give different weights, then you so what exactly is this achieving? Okay, that's what you have to make it very clearly. It's not that every solution that maxat gives is a Pareto optimal solution, is it?
Yes, every solution returned by the maxat problem is a Pareto optimal solution.
Yeah, but then why not just keep enumerating and then doing? Why do you do it like this?
Because for that it will be too expensive because
Yeah,
it will go into
but here you can do this divide, but there's no guarantee that you will
yes
always
yes
find parallel.
yes
See,
yes yes
that is the overview that you have to give. See, without actually, first you're done. Okay, theoretically, maxat gives you all the Pareto optimality. Okay, then now you're defining a more better solution. Just like Aritra is still there. Is he there? Huh?
yes sir.
Yeah. So I'm just drawing a parallel. See, he had a naive solution which enumerated the whole thing. Okay, but in his case, that was not giving maximal. Okay, here maxat at least is able to give maximal. Yeah, a solution, but there are too many. Therefore, you're devising an algorithm or a procedure to get to one of the maxat more efficiently to something which is as close to Pareto optimal as possible. Okay,
Yes.
explain that. Okay, what that thing is. See, before you actually do this in a simple slide in words, some bullets, say what is it that you're trying to do now? Because maxat itself, you can keep enumerating until hell freezes over. Okay, that is not possible.
Yes.
Therefore, now I'm devising. Okay, and then you
Yes. I'll mention this then.
which you have already had in the outline. Now you're getting that, so that the audience will know where are you headed. Okay, and
Yes.
that is what you're doing it here. Now, quickly go through the slides. Okay.
Yes. So this is the idea that
Okay.
split over all the regions and show like I can go to which regions and so on and so forth.
Yeah. Good. Yeah.
And this is how I will end up having like Pareto optimal interpretations. Now I also want some statistical guarantees for like the black box models as in terms of the number of.
What is the disadvantage of the previous thing? There is no guarantee that it will return all these dots. It may end up. Is that guaranteed to always converge into something which is, yeah, I guess if you keep dividing those squares smaller and smaller, eventually you will get to it, correct?
Yes.
Yeah, but so that itself can take a long time, right? Yeah.
Yes. So we have to what we do is we find some approximate solution in the sense that our size of the squares would be bounded by some figure.
Yeah, then you will get somewhere close to it. Yeah.
Yes.
Yeah, that you explain. Okay. And what is the guarantee? Yeah. So where is the algorithm there? Is there an algorithm description?
So I have given a very informal algorithm description.
Yeah, I think this is fine. This is fine. Yeah.
Yes. So this is the description.
Okay.
And then I move to a new thing, the last thing, that the statistical guarantees. Like if I have to like sample everything, so like that can give me efficient guarantees. Like, but that is not possible because that is impractical because of the size constraints. So the question is, what bounds on the sample size do we acquire that also prevents overfitting? And the answer comes from probably approximately correct learnability, which guarantees basically with some kind of confidence interval and some kind of error. If I just use size m samples, my job is
I
done.
get an idea. How many slides you have on this? This one, no?
And just how it fits in. This is like how is a
If you're
formula and
running
how it
out
fits
of
in.
time, I'd rather that you just skip over this, okay? The
Okay.
details of the statistical guarantee and say
Okay.
that they use this method to give certain guarantees and then concentrate on experiments. Okay?
Yes. So the experiment part I haven't included yet.
Yeah.
Like
Yeah,
I
I
will
trust
include
you.
it.
I trust you, and you can include it. Yeah.
And
Now,
yes,
one
and
other suggestion that I have is
sure.
when you show those encoding, those formulas are quite complicated. Okay.
Yes.
Is it possible to just use the your example to see how that can be encoded for that example?
As in with regards
Actual
to any say
formula.
one
Actual
example.
formula.
Yes.
Yeah,
So
use
maybe.
the second one, not the too complicated one. Maybe use the second one, okay? And show, write out, you work it out and then show. Is it possible?
Okay.
Huh?
Yes, I think I can do that.
Yeah, it may be too large for the biggest one, okay? I don't know. I
Yes,
mean,
I
that's
understand
one
that.
suggestion I have because it'll take a long time for you to describe this unless you practice, okay? What each of these means and so on. Okay, you have to write it out, okay? And then show, okay? But if you have an example, then even though people will most likely will not understand, okay, completely what you're saying here, okay? So you just have to say this part, this part, this part captures this, and then show it for
Sure.
on an example. Then
Sure.
it will be
So
faster.
just one thing, Professor.
Yes, yes.
So the first line in for every formula, like in English, describes what it does. So I will include that just English description, and instead of doing the formula, I will use my diagram, and then I will just write what the
I'm
formula is for
okay
the
with you.
diagram.
You can have this, okay? You can have the whole formula. That's fine. I mean, you already have a single description, huh? This line, what this captures.
Yes, yes, yes.
What does each of them capture?
Yes. So the first statement tells me that if this is true, lambda IP is true, that means node I has label P, and every label has exactly one P, one label.
Uh, uh, every node has exactly one label. Yes. Okay.
Yes.
Good, good.
Yes. That is the
Yeah.
first one.
The second
Second
one?
is a transition constraint given two nodes. What branching function I use to reach the jth node from the ith node. And the third is consistency that
Yeah, this is kind of relating two nodes. Yeah.
yes.
Yeah,
And third,
this is defining kind of an edge, okay? When you can have an edge, yeah?
yes,
Between those things, yes. And the third one? And the
that
third one?
defines the
Yeah,
branch. Yeah, only give the branching of predicates.
only branching predicates. C max is equal to maximum branching. So it allows, the number of branchings will have to be bounded by that maximum branch,
Yes,
correct?
yes.
Okay, that's what it is. Yeah, good. So these are syntactic constraints, yeah? And after that, you can simply say, if you could have it, yeah, even describing it like this, you have it organized well, okay? So showing after this, how these things will happen for a simple example. The second example, okay, the intermediate example might be useful, okay?
Okay,
And how
okay.
to encode by S? Go ahead, yeah.
Yes.
Yeah, just show me quickly.
So basically, S tells me ki, if it uses variables called MIS that tells me S is a sample from S, like the set of samples that is true if and only if node I occurs along some valid computation path on the input that is consistent with the output.
Got it.
So the
Okay.
leaves will have indices like this, and the
Yes.
nodes are true when the valid path
Yeah.
exists with
Yeah.
I to leaf.
Yeah. Indeed, when you follow that path, the output will correspond to what it is in the sample. correct?
Yes, 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 yes.
Good. Yeah. So
Yes.
I think you have everything done. Okay. Then what is the other two things? Yeah.
Yes. So here I use that same M predicate from what I used in previous slides,
Hmm.
and that I now want to maximize the number of sorry. Now I want to maximize the number of samples that get it correct.
Hmm.
So that is why I encoded it as soft clause with weights 1.
Hmm.
And lastly, this is the
No, 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 no,
explainability.
no, no. I kind of got distracted. So this one says, given a specific value of C and E,
Hmm.
that indeed, and some weights for the predicates, right?
Hmm.
For all the predicates, that indeed, no, no, no. This is
No, we do
delta
not
C. This is
bother with
delta C,
weights here.
correctness. Oh, this is not weights. Okay. Delta C is correctness. That it actually encodes that your correctness measure is indeed that ratio, correct?
Hmm.
That's what it encodes, right?
Yes.
But what do you mean by fixed weight is equal to 1? I don't
So,
understand.
so I have to, since this is a soft clause, I have to give some weight to this.
That weight. Okay, okay. Now you had to be careful here. Okay, you also have weights for the predicate. Don't confuse. Okay, so this
Yes.
is you're weighting this
So
clause.
I mentioned weight here because here the weight of the predicate is not involved.
Yeah, that's fine. Okay, but in words emphasize that. But
Yes, yes.
why are you giving it 1 as opposed to something else?
So that like I just can focus on, so the if I want to maximize this, I will just maximize the number of samples. I do not like discriminate between what samples are getting.
Yeah, you're not discriminating between any individual samples. Therefore, you
Hmm.
are, the more number of clauses for which it will be correct, so your accuracy will be higher, right? Yeah,
Yes, yes, yes.
yeah. Okay. Hmm.
And finally, like how to encode like the explainability measure. Here I have weights that are consistent with user preferences.
Hmm.
Each soft clause has a weight that is consistent with the user preferences for each predicate. And
Okay. Yeah, I
yeah,
think you have it done correctly. And if you add at least for maybe not for all of them, but some of them, what that would be with a formula, it would be very clear. Yeah. Uh,
okay,
and you don't even need to go through this itself. Okay. Here, when you describe, you just describe in English. Okay. You don't need to go through the syntax. Okay.
sure, sure.
This exact formula, which will be covered by your showing that for the exam. Yeah.
Yes.
Then it is quite good. Yeah. No, no, I'm quite happy with your thing. Yeah. Yeah.
Thank you.
Yeah.
Okay. So this is it.
Yeah.
Also,
I'm going to stop live stream.